In LeetCode problem 18, for a sum, we're not just crunching numbers, we're filtering signal from noise, like detecting fraud, optimizing joins, or fusing sensor data. With up to 200 inputs and values near a billion, brute force quickly crashes and burns. But what if we could dodge all that wasted work? Let's dive in. All right, ducklings, wings out. We're splashing straight into brute force, trying every combination to uncover those elusive quadruplets. First things first, we grab the array length so we can safely bound our loops. To ensure each quadruplet is unique, we'll store sorted versions in a set, since sets ignore duplicates automatically. We kick things off by anchoring the first number. This becomes the base of our quadruplet search. Next, we lock in the second number. This sets up all possible pairs starting after the first index. Then we pick the third number, making sure we move forward to keep all indices distinct. Finally, we choose the fourth number. With all four in hand, it's time to check if their sum hits the target. Because the values can get huge, we cast along to safely compare the total against the target. When we hit a match, we gather those numbers, sort them, and prep to store them in the set. Order doesn't matter, but consistency does. If the sorted quadruplet is already in the set, it's ignored. Sets handle that automatically. After exhausting all combos, we convert the set back into a list and send it off. This brute force method runs in big O of n to the fourth, up to 1.6 billion steps for 200 elements, and the set costs us big O of n squared in space. It's slow, clunky, and risky for overflow, but it's a good baseline for exploring the problem space. So how do we skip the waste? What if we sort first and prune early? That lets us reject duplicates and steer more directly. Time to bring in the two-pointer strategy for a serious upgrade. We start clean with a result list. If the array is null or has fewer than 4 elements, we return it, since we can't form a valid quadruplet anyway. Next, we sort the array. This unlocks two-pointer logic and makes it easier to dodge duplicate entries. Our outer loop sets the first number and skips over any repeat to keep results clean. Then we nest another loop to pick the second number, again checking for duplicates to stay efficient. With the first two locked in, we drop in 2 pointers, one right after the second index and one at the array's end. This combo lets us scan pairs efficiently. Inside the loop, we compute the sum of all 4 numbers, again using long to avoid any overflow issues. If the sum matches the target, we add the quadruplet to our result and skip over any duplicates before moving the pointers inward. If the sum's too small, we shift the left pointer right, looking for a bigger number. If the sum's too big, we pull the right pointer left, searching for something smaller. Once we've tried every valid combo, we return the result list with all matching quadruplets. This optimized method runs in big O of n cubed, about 8 million steps for 200 elements. Much faster than brute force. Space is constant aside from output. It's more structured and readable, with only a small cost for sorting. Still, even this checks more combos than we need. Can we go deeper? Let's try a general recursive strategy, a flexible k-sum approach that scales. First, we sort the array. That gives us duplicate control and enables two-pointer logic later on. Since we're solving for sum, we'll delegate the work to a k-sum method, starting with k equal to 4 and the full target. Inside k-sum, we initialize a list to store all valid combinations that add up to the target. If we've narrowed it down to 2 elements, we hand things off to a dedicated to-sum method that uses 2 pointers. Otherwise, we loop through the array from the current index. For each element, we recursively search for k-1 numbers that hit the reduced target. To stay efficient, we skip over duplicate values by checking if the current number matches the previous one. In each recursive call, we reduce the array window and subtract the current number from the target, shrinking the problem step by step. For every smaller solution we get back, we tack on the current number and add the full combo to our results. Once we've explored all paths at this recursion level, we return the collected combinations. Now for the to-sum helper. We initialize an empty result list and set up 2 pointers, one low and one high. We loop while the pointers haven't crossed, calculating the sum of the pair and comparing it to the target. If they match, we store the pair and skip over any duplicates on both sides before continuing. If the sum's too small, we nudge the left pointer right. If it's too large, we drag the right pointer left. When the two-pointer scan is done, we return the list of valid two-number combinations. This recursive approach runs in big O of n to the k-1 so for 4 sum, that's still n-cubed. Space is big O of k for the recursion stack. It's clean, scalable, and great for interviews or real-world use where modularity matters. We kicked things off with brute force, slow and memory heavy, then stepped up with sorting and two pointers, slicing away redundancy and reaching n-cubed time. But the real win, the recursive k-sum. It solves 4 sum cleanly and generalizes effortlessly. This isn't just a clever trick, it's a framework used in systems from search engines to event analytics. Mastering it arms you with a powerful pattern. Think you can extend it to 5 sum? 6 sum? Start there and keep your code base sharp. See you next time.